Hello there, and welcome to the Sleepy Library. It's lovely to have you here tonight. Before we begin, I'd love to know where in the world you're watching from. Perhaps you're tucked in beneath a warm blanket, or maybe you're listening from a quiet corner of your home with a cup of tea nearby. Wherever you are, I hope you're comfortable and ready to settle in for a slow, gentle journey through one of nature's most beautiful wonders. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel keep going. And to those of you already subscribed, thank you. Your support means more than you know. Tonight, we're going to explore something truly special. Something that has captured the imagination of people for thousands of years. Something that hangs in the night sky like curtains of colored light, dancing and shimmering across the darkness. We're going to talk about the Northern Lights, also known by their scientific name, the Aurora Borealis. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake. But if it does, at least you'll have a better understanding of how our planet and the sun work together to create one of the most breathtaking displays in all of nature. A small price to pay for a restless night, perhaps. So, let's begin, shall we? The Northern Lights are always there, happening somewhere above our planet. Right now, as you listen to these words, somewhere near the Arctic, there might be ribbons of green and purple light swaying across the sky. They don't follow a schedule we set. They don't wait for anyone to be watching. They simply exist. A quiet conversation between the sun and earth that's been going on for billions of years. When we look up at the night sky on most evenings, we see darkness punctuated by stars. The stars appear as tiny points of light, steady and unchanging. But the aurora is different. It moves, it flows, it shimmers and pulses like something alive. Sometimes it appears as a gentle glow on the horizon. Other times, it explodes across the entire sky in waves of color that seem to roll from one edge of your vision to the other. People who live in places where the Northern Lights appear regularly will tell you that no two displays are ever quite the same. One night, you might see a faint green arc hanging low in the northern sky, barely visible. The next night, the entire heavens might fill with brilliant curtains of light that change from green to pink to purple in the space of minutes. The aurora has its own rhythm, its own moods, its own way of expressing the invisible forces at work in the space around our planet. For thousands of years, humans have watched these lights and wondered. Long before we understood atoms or magnetic fields or solar wind, people looked up at the dancing colors and created stories to explain them. Some cultures believed the lights were spirits. Others thought they were reflections of great fires in the distance. In some traditions, the aurora was seen as a bridge between worlds, a path that connected the living to something beyond. The Inuit peoples of northern Alaska have their own name for these lights in their language, a name that has existed for countless generations, passed down through oral tradition long before any scientist tried to explain what they were seeing. But here's the thing. As beautiful and mysterious as those old stories are, the truth about what creates the Northern Lights is even more wonderful. Because the aurora isn't just a pretty light show. It's evidence of something much larger. It's a visible sign of the constant stream of energy flowing from the sun. It's proof that our planet has a protective shield around it. And it's a reminder that we live in a solar system that is alive with forces we can't see, but that shape everything about our existence. The aurora happens at altitudes far above where airplanes fly, far above where weather happens. Up in a region of the atmosphere so high and so thin that it barely qualifies as air at all. And yet, the light produced up there is bright enough to illuminate the landscape below, bright enough to read by in some cases, bright enough to cast shadows on the snow. Think about that for a moment. Something happening hundreds of miles above your head can light up the ground beneath your feet. That's how powerful these processes are. And it's happening all the time. Even when you can't see it, even during daylight, even during summer, when the sky never gets dark enough in the far north, the particles are still arriving from the sun, the collisions are still occurring, the light is still being produced. It's just that we can only see it when conditions are right, when the sky is dark enough and the activity is strong enough, and we happen to be looking in the right direction. Let's start at the very beginning of this story, at the place where the energy for the northern lights originates. Let's start with the sun. The sun is not a quiet, stable ball of light. From Earth, it might look calm and constant, rising each morning and setting each evening with perfect predictability. But if you could look at the sun more closely, you would see that it's actually a churning, boiling cauldron of energy. The sun's surface is constantly moving, constantly changing, constantly sending material out into space. Deep inside the sun's core, something remarkable happens. The temperature there reaches about 15 million degrees. The pressure is so extreme that atoms can't maintain their normal structure. Hydrogen atoms, the simplest and most abundant element in the universe, are forced together despite their natural tendency to repel each other. When the conditions are extreme enough, these hydrogen atoms fuse together to create helium. This process is called nuclear fusion, and it releases enormous amounts of energy, more energy than you can imagine. Every second, the sun converts about 600 million tons of hydrogen into helium. And every second, about 4 million tons of matter gets converted into pure energy. That energy gradually makes its way from the core to the surface. It's not a quick journey. The energy bounces around inside the sun, getting absorbed and re-emitted countless times. It can take tens of thousands of years, maybe even hundreds of thousands of years, for energy created in the core to finally reach the surface. When it finally does reach the surface, it radiates outward as light and heat. This is the sunlight that warms Earth, that makes plants grow, that powers the water cycle and the weather and all of life on our planet. But that's not all the sun sends our way. The sun also produces something called the solar wind. Despite its name, the solar wind has nothing to do with air or weather. It's actually a stream of tiny particles, mostly electrons and protons, that flow constantly away from the sun in all directions. These particles come from the sun's corona, which is the outermost layer of the sun's atmosphere. The corona is incredibly hot, even hotter than the visible surface of the sun. In fact, scientists are still trying to fully understand why the corona is so hot. But this intense heat gives particles enough energy to escape the sun's gravity and stream out into space. These particles travel incredibly fast, racing through space at speeds between about 250 and 500 miles per second. That's roughly 1 million miles per hour on average. To give you some perspective, that's fast enough to travel from Earth to the Moon in less than 15 minutes. The solar wind fills the entire solar system. It flows past Mercury, past Venus, past Earth, all the way out beyond the orbit of Pluto and into interstellar space. Everywhere the sun's influence reaches, the solar wind is flowing. The sun has been sending this solar wind into space for billions of years. It never stops. Even on the quietest days, when the sun appears calm from Earth, the solar wind is still flowing outward, filling the entire solar system with particles. These particles are electrically charged, which means they carry a tiny amount of electric energy with them. Electrons have a negative charge. Protons have a positive charge. And when billions upon billions of these charged particles flow through space together, they create an electric current. They also carry with them a magnetic field, frozen into the flow like patterns in a river. Now, the sun doesn't release the same amount of particles all the time. Sometimes the solar wind is gentle and steady, flowing at a relatively calm pace. Other times, it becomes much more intense, with particles flowing faster and in greater numbers. This variability happens because the sun itself is not constant. The sun is a dynamic object, with its own complex behavior patterns. The sun goes through cycles of activity that last about 11 years. These are called solar cycles, and astronomers have been tracking them for more than 150 years. During these cycles, the sun's magnetic field becomes twisted and tangled. This happens because the sun doesn't rotate as a solid body. Different parts of the sun rotate at different speeds. The equator rotates faster than the poles. This differential rotation wraps the magnetic field lines around and around, like winding up a rubber band. As the magnetic field becomes more twisted, strange things start happening at the sun's surface. Dark spots appear. These spots are called sunspots, and they mark places where the sun's magnetic field has become especially strong and complex. Sunspots look dark because they're actually cooler than the surrounding surface, though they're still incredibly hot by any normal standard. A typical sunspot might have a temperature of about 6,500 degrees, compared to about 10,000 degrees for the normal solar surface. During the peak of a solar cycle, called solar maximum, the sun might have dozens or even hundreds of sunspots at a time. During the quiet part of the cycle, called solar minimum, there might be no sunspots at all for days or weeks. We're currently in a phase of higher activity. Solar cycle 25 began in December of 2019, and it reached its peak in October of 2024. This means that right now, the sun is quite active, with frequent sunspots and lots of activity happening on its surface. When the magnetic fields around sunspots become too twisted, too stressed, they can suddenly release their energy in dramatic events. Sometimes this happens as a solar flare, which is a sudden, intense burst of radiation across the entire electromagnetic spectrum. Solar flares release as much energy as millions of nuclear bombs exploding simultaneously. They produce intense X-rays and ultraviolet light that can reach Earth in just 8 minutes, traveling at the speed of light. But there's another type of solar eruption that's even more important for creating auroras. These are called coronal mass ejections. When the magnetic field around a sunspot releases its energy, it can actually throw material off the sun's surface. Not just radiation, but actual matter. Billions of tons of plasma, which is superheated gas made of charged particles, gets hurled into space. These clouds of plasma expand as they travel, growing larger and larger. By the time they reach Earth, they can be enormous, larger than the planet itself. Coronal mass ejections don't travel at the speed of light like solar flares do. They're made of matter, actual particles with mass, so they travel much slower. A typical coronal mass ejection might move at speeds between 1 million and 7 million miles per hour. That sounds incredibly fast, and it is. But it's still slow enough that it takes time for the cloud to reach Earth. Usually somewhere between 15 hours and 3 days, depending on how fast the ejection is moving. This travel time is actually useful because it gives us warning. Scientists can see a coronal mass ejection leave the Sun and can calculate whether it's aimed at Earth. If it is, they can predict roughly when it will arrive. This gives us time to prepare, to protect satellites, to alert power companies, to take precautions. But it also gives aurora watchers time to get excited, because when a strong coronal mass ejection reaches Earth, it almost always produces spectacular auroras. Not every coronal mass ejection hits Earth. The Sun is throwing these clouds of plasma out in all directions, and Earth is a relatively small target in the vastness of space. Most coronal mass ejections miss us completely. But a few times each month during solar maximum, a coronal mass ejection does head our way, and when it arrives, something magical happens. But before we get to the magic, we need to understand something important about our planet. Earth has a shield. You can't see it or feel it, but it's there, surrounding our planet like a protective bubble. This shield is called the magnetosphere, and it's created by Earth's magnetic field. You might remember learning about magnets in school. If you've ever played with a bar magnet, you've seen how it can attract certain metals, and how it has a north pole and a south pole. You've probably seen how iron filings arrange themselves in curved lines around a magnet, showing the invisible magnetic field. Earth works like a giant magnet. Deep inside our planet, about 2,000 miles below the surface, there's a layer of molten iron. This layer is called the outer core, and it's constantly moving and flowing. The movement happens because of heat. The inner core of Earth is solid and incredibly hot. The outer core, surrounding it, is liquid metal, mostly iron with some nickel mixed in. Heat from the inner core causes convection currents in the outer core, making the liquid metal flow in complex patterns. Now, here's where it gets interesting. Iron is a good conductor of electricity. When liquid iron moves through an existing magnetic field, it generates electric currents, and those electric currents in turn generate more magnetic field. This creates a self-sustaining process called a dynamo. The moving liquid iron in Earth's outer core acts like a giant dynamo, constantly generating Earth's magnetic field. This magnetic field extends far out into space. If you could somehow sprinkle iron filings around Earth the way you can around a bar magnet, you would see invisible lines of magnetic force extending from the North Pole to the South Pole, looping through space in graceful curves. These magnetic field lines create a boundary between Earth and the rest of space. They form a kind of bubble around our planet that scientists call the magnetosphere. The magnetosphere is huge. On the side facing the Sun, it extends about 40,000 miles into space. That's about 6 Earth diameters. On the side facing away from the Sun, it stretches even farther, reaching out more than 400,000 miles into space, farther than the distance from Earth to the Moon. This elongated shape happens because of the solar wind pushing against one side while stretching out the other side. The magnetosphere looks a bit like a teardrop or a comet, with a rounded front and a long tail streaming behind. Now, here's where it gets interesting. The magnetosphere doesn't just sit there doing nothing. It interacts with the solar wind. When the stream of charged particles from the Sun encounters Earth's magnetic field, something complex happens. Most of the particles get deflected. They flow around the magnetosphere like water flowing around a rock in a stream. The sun's particles push against one side of Earth's magnetic field, compressing it. On the other side, away from the sun, the magnetic field gets stretched out into that long tail. This interaction is crucial. Without the magnetosphere, the solar wind would hit Earth's atmosphere directly. Over time, it would strip away our atmosphere, removing the protective layer of air that makes life possible on our planet. We know this can happen because we've seen it happen elsewhere in our solar system. Mars, for example, once had a thicker atmosphere than it does today. Scientists have found evidence that Mars once had liquid water on its surface, which means it must have had a much denser atmosphere to keep that water from boiling away. But Mars lost its magnetic field billions of years ago. Without that protective shield, the solar wind slowly removed much of the Martian atmosphere. Today, Mars has an atmosphere less than 1% as thick as Earth's. The solar wind accomplished this over billions of years, particle by particle, gradually stripping away the air. Earth's magnetosphere protects us from this fate. It deflects most of the solar wind, keeping it from reaching our atmosphere. But the magnetosphere isn't perfect. It has weak spots. It has places where the solar wind can sometimes get through, and those weak spots are where the magic happens. The weakest points in Earth's magnetosphere are at the north and south poles. This happens because of the shape of the magnetic field. Remember those field lines we talked about? The ones that loop from pole to pole? Well, at the poles, those field lines come together. They converge. Instead of creating a closed barrier, they create funnel-shaped openings. Think of it like this. Imagine you're holding an umbrella in the rain. Most of the rain hits the umbrella and runs off the sides, but there's a small opening at the top where the handle goes through. A few raindrops might get through there. Earth's magnetosphere works similarly. Most of the solar wind flows around the sides, but some particles can funnel through near the poles. When a coronal mass ejection from the sun reaches Earth, it doesn't just bounce off the magnetosphere. Interaction is more complex than that. The cloud of particles and magnetic field from the sun slams into Earth's magnetosphere. This creates waves and disturbances that travel through the magnetosphere like ripples on a pond. The magnetosphere gets compressed on the sunward side and stretched even farther on the night side. And crucially, some of the particles find their way through those funnel-shaped openings at the poles. The process that allows particles through is called magnetic reconnection. This happens when the magnetic field carried by the solar wind has an orientation opposite to Earth's magnetic field. When opposite magnetic fields meet, they can cancel each other out temporarily, creating a temporary opening. It's like two magnets pushing against each other until one flips around. When this happens, particles from the solar wind can suddenly flow through the opening and into Earth's magnetosphere. Once the particles get through, they don't just crash straight into the atmosphere. Instead, they get caught by Earth's magnetic field lines. Remember, these particles are electrically charged, and charged particles interact with magnetic fields in specific ways. The magnetic field forces the particles to spiral along the field lines, following those invisible curves that extend from one pole to the other. The particles spiral down toward Earth's atmosphere, guided by the magnetic field like water spiraling down a drain. This is a crucial moment in the creation of the aurora. The charged particles from the sun are now entering Earth's atmosphere, guided by invisible lines of magnetic force. They're traveling incredibly fast, still moving at hundreds of miles per second. They're carrying enormous amounts of energy, and they're about to collide with something. High above Earth's surface, at altitudes between about 60 and 600 miles up, the atmosphere is very thin. At sea level, Earth's atmosphere contains about 25 quintillion molecules in every cubic inch. That's 25 followed by 18 zeros. Up at aurora altitudes, the atmosphere might contain only 10 million molecules per cubic inch. That's still a lot, but it's about 1 trillion times less dense than at sea level. The air up there is so thin that you could barely call it air at all. It's almost a vacuum. Almost, but not quite. There are still atoms and molecules floating around in this region, mostly oxygen and nitrogen, the same elements that make up the air we breathe, just spread much farther apart. At lower altitudes, oxygen exists mostly as molecules, two atoms bonded together. But up at aurora altitudes, where the air is very thin, oxygen can exist as individual atoms. The ultraviolet light from the sun breaks apart oxygen molecules during the day, and at night, the aurora continues this process. When the fast-moving particles from the sun collide with these atoms and molecules of oxygen and nitrogen, something wonderful happens. The collision gives the atoms extra energy. It excites them. An electron in the atom gets knocked into a higher energy level. But atoms don't like to stay in this excited state. It's unstable. The electron wants to fall back down to its normal energy level. And when it does, it has to release that extra energy somehow. The way it releases that energy is by giving off light. A tiny packet of light called a photon. Each individual photon is incredibly small, far too small to see on its own. But when billions and billions of atoms do this at the same time, all releasing photons, all releasing light, those photons together create a glow bright enough to see from the ground. That glow is the aurora. The northern lights are literally the Earth's atmosphere lighting up in response to energy from the sun. It's Earth saying, "I received your message," in the language of light. But why do we see different colors? Why is the aurora sometimes green, sometimes red, sometimes purple or blue or pink? The color depends on which atoms are getting excited and at what altitude the collisions are happening. It's a bit like how different elements produce different colors when they burn. If you've ever seen a fireworks display, you know that different chemicals create different colored sparks. Copper compounds burn blue-green, strontium compounds burn red, sodium compounds burn yellow. The same principle applies to the aurora, except instead of burning, we're exciting atoms with high-energy particles. The most common color in the northern lights is green. This soft, almost luminous green appears more frequently than any other color, and it's one of the easiest aurora colors for human eyes to detect. Our eyes are most sensitive to green light, more so than to red or blue. This makes sense from an evolutionary perspective. Our ancestors needed to see well in forests and grasslands, where green is the dominant color. So our eyes evolved to be particularly good at detecting different shades of green. This means that even a relatively weak aurora can be visible if it's producing green light. Green light in the aurora comes from oxygen atoms. Specifically, it comes from oxygen atoms that have been excited by collisions with solar particles at altitudes between about 60 and 150 miles above Earth's surface. When an oxygen atom at this altitude gets struck by a high-energy particle, it enters what scientists call an excited state. One of its electrons has been knocked into a higher energy level. Now, that electron wants to fall back down to its normal level, but it can't do so instantly. Oxygen is particular about how it releases energy. An excited oxygen atom takes about 1 second to release its energy and return to its normal state. 1 second might not sound like much. In everyday life, 1 second passes in a blink. But at high altitudes, where the air is very thin, 1 second is actually quite a long time. It's long enough that the oxygen atom can release its photon before bumping into another atom. At lower altitudes, where the air is denser, the oxygen atom would collide with another particle before it could emit light. The collision would rob it of its energy without producing any light. But at auroral altitudes, the air is thin enough that the oxygen atom has time to emit its photon. And the photon it emits? A beautiful, soft green with a wavelength of about 558 nanometers. This is right in the middle of the visible spectrum, right where our eyes are most sensitive. When thousands upon thousands of oxygen atoms do this together across a broad area of the sky, they create those characteristic green curtains of light that are the signature color of the aurora. The green can range from a pale, almost white green to a vibrant, almost neon green, depending on how much energy the atoms are receiving and how many atoms are being excited. The sun is not a quiet, stable ball of light. From Earth, it might look calm and constant, rising each morning and setting each evening with perfect predictability. But if you could look at the sun more closely, you would see that it's actually a churning, boiling cauldron of energy. The sun's surface is constantly moving, constantly changing, constantly sending material out into space. Deep inside the sun's core, something remarkable happens. The temperature and pressure are so extreme that hydrogen atoms are forced together to create helium. This process is called nuclear fusion, and it releases enormous amounts of energy. That energy gradually makes its way from the core to the surface, taking thousands of years to complete the journey. When it finally reaches the surface, it radiates outward as light and heat. But that's not all the sun sends our way. The sun also produces something called the solar wind. Despite its name, the solar wind has nothing to do with air or weather. It's actually a stream of tiny particles, mostly electrons and protons, that flow constantly away from the sun in all directions. These particles travel incredibly fast, racing through space at speeds of about 1 million miles per hour. To give you some perspective, that's fast enough to travel from Earth to the Moon in less than 15 minutes. The sun has been sending this solar wind into space for billions of years. It never stops. Even on the quietest days, when the sun appears calm from Earth, the solar wind is still flowing outward, filling the entire solar system with particles. These particles are electrically charged, which means they carry a tiny amount of electric energy with them. And when billions upon billions of these charged particles flow through space together, they can interact with magnetic fields in interesting ways. Now, the sun doesn't release the same amount of particles all the time. Sometimes the solar wind is gentle and steady. Other times, it becomes much more intense. This happens because the sun goes through cycles of activity that last about 11 years. During these cycles, the sun's magnetic field becomes twisted and tangled. Dark spots appear on the sun's surface. These spots are called sunspots, and they mark places where the sun's magnetic field has become especially strong and complex. When these magnetic fields become too twisted, something dramatic can happen. They can suddenly release huge amounts of energy in the form of what scientists call a coronal mass ejection. Imagine if you took a giant piece of elastic and stretched it and twisted it until it couldn't hold any more tension. Then, imagine it snapping back all at once, releasing all that stored energy in an instant. That's similar to what happens during a coronal mass ejection. These ejections throw enormous clouds of particles into space. We're talking about billions of tons of material moving at millions of miles per hour. If one of these clouds happens to be aimed in Earth's direction, it will take somewhere between 15 hours and 3 days to reach us, depending on how fast it's moving. And when it arrives, something magical happens. But before we get to the magic, we need to understand something important about our planet. Earth has a shield. You can't see it or feel it, but it's there, surrounding our planet like a protective bubble. This shield is called the magnetosphere, and it's created by Earth's magnetic field. You might remember learning about magnets in school. If you've ever played with a bar magnet, you've seen how it can attract certain metals and how it has a north pole and a south pole. Earth works like a giant magnet. Deep inside our planet, there's a layer of molten iron that moves and flows. This moving iron creates electric currents, and those electric currents generate a magnetic field that extends far out into space. If you could somehow sprinkle iron filings around Earth, the way you can around a bar magnet, you would see invisible lines of magnetic force extending from the North Pole to the South Pole, looping through space in graceful curves. These magnetic field lines create a boundary between Earth and the rest of space. They form a kind of bubble around our planet that scientists call the magnetosphere. Now, here's where it gets interesting. The magnetosphere doesn't just sit there doing nothing. It interacts with the solar wind. When the stream of charged particles from the sun encounters Earth's magnetic field, most of them get deflected. They flow around the magnetosphere like water flowing around a rock in a stream. The sun's particles push against one side of Earth's magnetic field, compressing it. On the other side, away from the sun, the magnetic field gets stretched out into a long tail that extends far into space. Without this magnetic shield, the solar wind would strip away Earth's atmosphere over time. The particles would gradually remove the protective layer of air that makes life possible on our planet. We know this can happen because we've seen it happen elsewhere in our solar system. Mars, for example, once had a thicker atmosphere than it does today. But Mars lost its magnetic field billions of years ago, and over time, the solar wind slowly removed much of the Martian atmosphere. So Earth's magnetosphere protects us. It keeps the solar wind from harming our atmosphere. But the magnetosphere isn't perfect. It has weak spots, and those weak spots are where the magic happens. The weakest points in Earth's magnetosphere are at the north and south poles. This happens because of the shape of the magnetic field. Remember those field lines we talked about? The ones that loop from pole to pole? Well, at the poles, those field lines come together. They converge. They create funnel-shaped openings where the solar wind can sometimes get through. When a coronal mass ejection from the sun reaches Earth, it doesn't just bounce off the magnetosphere. Some of the particles find their way through these funnel-shaped openings at the poles. The particles follow the magnetic field lines, spiraling down toward Earth's atmosphere like water swirling down a drain. This is a crucial moment in the creation of the aurora. The charged particles from the sun are now entering Earth's atmosphere, guided by invisible lines of magnetic force. They're traveling incredibly fast, carrying enormous amounts of energy, and they're about to collide with something. High above Earth's surface, at altitudes between about 60 and 200 miles up, the atmosphere is very thin. The air up there is nothing like the air we breathe. It's so thin that you could barely call it air at all. But there are atoms and molecules floating around in this region, mostly oxygen and nitrogen, the same elements that make up the air we breathe, just spread much farther apart. When the fast-moving particles from the sun collide with these atoms and molecules of oxygen and nitrogen, something wonderful happens. The collision gives the atoms extra energy. It excites them. And when atoms get excited like this, they have to release that extra energy somehow. The way they do it is by giving off light. Think about it like this. Imagine you're holding a ball. If someone throws another ball at the one in your hand, the impact might knock your ball out of your hand. It might bounce or fly away. The atoms in Earth's upper atmosphere work in a similar way. When a high-energy particle from the sun strikes an atom, it can knock an electron into a higher energy level. But that electron doesn't want to stay in that high-energy state. It wants to fall back down to its normal level. And when it does, it releases the extra energy as a tiny packet of light called a photon. When billions and billions of atoms do this at the same time, releasing billions of tiny photons, those photons together create a glow bright enough to see from the ground. That glow is the aurora. The northern lights are literally the Earth's atmosphere lighting up in response to energy from the sun. But why do we see different colors? Why is the aurora sometimes green, sometimes red, sometimes purple or blue or pink? The color depends on which atoms are getting excited and at what altitude the collisions are happening. It's a bit like how different elements produce different colors when they burn. If you've ever seen a fireworks display, you know that different chemicals create different colored sparks. The same principle applies to the aurora. The most common color in the northern lights is green. This soft, almost luminous green appears more frequently than any other color, and it's one of the easiest aurora colors for human eyes to detect. Green light in the aurora comes from oxygen atoms. Specifically, it comes from oxygen atoms that have been excited by collisions with solar particles at altitudes between about 60 and 150 miles above Earth's surface. When an oxygen atom at this altitude gets struck by a high-energy particle, it enters an excited state. But oxygen is particular about how it releases that energy. An excited oxygen atom takes about 1 second to release its energy and return to its normal state. 1 second might not sound like much, but at high altitudes where the air is very thin, 1 second is actually quite a long time. It's long enough for the atom to emit its light before colliding with another particle. And the light it emits? A beautiful soft green with a wavelength of about 558 nanometers. When thousands upon thousands of oxygen atoms do this together, they create those characteristic green curtains of light that are the signature color of the aurora. But what about red? Red auroras are less common than green ones, but they're no less beautiful. Red light in the aurora also comes from oxygen atoms, but from oxygen atoms at much higher altitudes, typically above 150 miles. Up at these heights, the atmosphere is even thinner than it is lower down. Collisions between atoms happen less frequently, and this allows a different kind of light emission to occur. High-altitude oxygen atoms have another way of releasing energy. They can enter a different excited state, one that takes much longer to decay. We're talking about more than 100 seconds. That's nearly 2 minutes. For an atom to successfully emit light in this way, it needs to stay excited for all that time without colliding with another atom. This can only happen at very high altitudes, where the atmosphere is extremely thin. When these high-altitude oxygen atoms finally release their energy, they emit red light with a wavelength of about 630 nanometers. This creates the deep red glow that sometimes appears at the top of aurora displays, or occasionally fills the entire sky during very strong events. Purple and blue colors in the aurora come from nitrogen. Nitrogen molecules can emit light very quickly after being excited, much faster than oxygen atoms. This means nitrogen can contribute to the aurora even at lower altitudes, where the atmosphere is a bit denser and collisions happen more frequently. When nitrogen gets ionized, meaning when it loses an electron, it can emit blue and purple light. When neutral nitrogen molecules get excited, they can emit reddish-purple light. The purple and blue colors often appear at the lower edges of aurora curtains, creating a colorful border along the bottom of the display. Sometimes you might see pink, which is actually a combination of red from nitrogen and green from oxygen, blending together in a way that creates that soft, rosy hue. The colors can change as you watch. An aurora might start as a faint green glow, then intensify and develop red tops, then shift to include purple edges. The colors depend on which atoms are being excited, how much energy they're receiving, and at what altitude the collisions are taking place. Each aurora is unique because the conditions are always changing. The solar wind varies, the Earth's magnetic field fluctuates, the composition of the atmosphere shifts slightly with altitude. All these factors come together to create a light show that is never quite the same twice. If you've ever been lucky enough to see the northern lights in person, you know they don't just sit still in the sky. They move, they flow, they shimmer and wave like curtains caught in a gentle breeze. This movement is one of the most mesmerizing aspects of the aurora. Sometimes the lights appear to pulse, brightening and dimming in a steady rhythm. Other times, they ripple across the sky in waves. Occasionally, they form spirals or rays that seem to converge toward a point directly overhead. Why do the northern lights move? The movement comes from changes in the flow of particles from the sun and variations in Earth's magnetic field. The solar wind isn't constant. It speeds up and slows down. It becomes denser in some regions and thinner in others. These variations affect how many particles are entering Earth's atmosphere at any given moment and where exactly they're entering. Earth's magnetic field also shifts and flexes. When the solar wind pushes against the magnetosphere, it can cause waves and disturbances that travel along the magnetic field lines. These disturbances change the path that particles take as they spiral down toward the atmosphere. As the paths change, the locations where the particles collide with atmospheric atoms change too. This creates the appearance of movement in the aurora. Scientists have discovered that the aurora can move quite fast. Individual features in an aurora display can travel at hundreds or even thousands of miles per hour across the sky. And yet, from the ground, the movement often appears gentle and graceful, like a slow dance performed by light itself. There's another interesting aspect to aurora movement. The northern lights and the southern lights, which we call the aurora australis, are mirror images of each other. They happen simultaneously on opposite sides of the planet. During a strong event, if you could somehow see both poles at once, you would notice that both auroras brighten at the same time, and their shapes roughly mirror each other across the equator. This happens because the same solar wind that creates the northern lights also creates the southern lights, and both are guided by Earth's magnetic field, which extends from one pole to the other. Not all nights are equal when it comes to seeing the northern lights. Some nights, the aurora is barely visible, just a faint glow on the northern horizon. Other nights, it fills the sky with brilliant, dancing colors. What makes the difference? The answer comes back to the sun and its cycle of activity. Remember how we mentioned that the sun goes through an 11-year cycle? During this cycle, the number of sunspots on the sun's surface rises and falls. When there are more sunspots, the sun is more active. When there are fewer sunspots, the sun is quieter. During periods of high solar activity, called solar maximum, the sun produces more coronal mass ejections and more solar flares. These events send larger and more powerful bursts of particles toward Earth. When these powerful bursts reach Earth's magnetosphere, they can create strong geomagnetic storms. These storms compress Earth's magnetic field and allow more particles to enter the atmosphere at the poles. The result is brighter, more active, and more widespread auroras. During solar maximum, the northern lights can sometimes be seen much farther south than usual. Normally, you need to be quite close to the Arctic to have a good chance of seeing the aurora. But during strong geomagnetic storms, the aurora can expand southward, appearing in places that rarely see it. There have been times when the northern lights were visible from places as far south as the Mediterranean Sea or the southern United States. One of the most powerful geomagnetic storms ever recorded happened in September of 1859. It's called the Carrington event, named after one of the astronomers who observed the solar flare that triggered it. During the Carrington event, auroras were seen around the world, even in tropical regions. The lights were so bright that people in the Rocky Mountains reportedly woke up thinking it was morning. Telegraph systems, the most advanced technology of the time, were disrupted or even set on fire by the electrical currents induced by the storm. If an event like the Carrington event happened today, it would cause much more widespread problems. Our modern world depends on technology that is vulnerable to geomagnetic storms. Power grids can be affected. Satellites can be damaged. Radio communications can be disrupted. GPS systems can lose accuracy. This is why scientists now carefully monitor the sun and try to predict when strong storms might occur. They want to give us warning so we can protect our technology. But here's something interesting. Even though strong storms can cause problems, they also create the most spectacular aurora displays. There's something bittersweet about that. The same solar events that can disrupt our technology also give us some of the most beautiful natural phenomena we can witness. During periods of low solar activity, called solar minimum, the aurora is still there. It never stops completely. But the displays tend to be weaker and more confined to regions very close to the poles. Even during solar minimum, though, if you're in the right place and the conditions align, you can still see the northern lights. They might be gentle and subtle, but they're there. A constant reminder of the connection between Earth and Sun. Right now, as of the time this information was gathered, we're in solar cycle 25, and the Sun reached its peak activity phase in October of 2024. This means we're in an excellent period for seeing auroras. The next few years should continue to offer good opportunities as the Sun remains active. Eventually, around 2030 or 2031, the Sun will reach solar minimum again, and aurora activity will become less frequent for a while. But then, the cycle will begin again, as it has for billions of years. For a long time, scientists understood the basic idea of how the northern lights form. They knew particles from the Sun collided with Earth's atmosphere. They knew this happened near the poles. They knew different atoms emitted different colors. But there was still a mystery. How exactly did the particles from the solar wind get accelerated to the high speeds needed to create auroras? In recent years, scientists made an important discovery. They found that the acceleration happens through a process involving what are called Alfvén waves. These are special types of waves that travel along magnetic field lines, kind of like waves traveling along a rope if you shake one end. When disturbances in the solar wind strike Earth's magnetosphere, they create these Alfvén waves. The waves travel along Earth's magnetic field lines toward the poles. And here's the really interesting part. Electrons in the space near Earth can catch these waves, almost like a surfer catching an ocean wave. If an electron is moving at just the right speed relative to the wave will pick it up and accelerate it to very high speeds. These surfing electrons then race down the magnetic field lines into Earth's atmosphere, where they collide with atoms and create the aurora. Scientists figured this out by doing clever experiments in laboratories here on Earth, recreating the conditions found in space and measuring how electrons and alpha waves interact. It was a breakthrough in our understanding of how the northern lights actually work at a detailed level. This discovery is a good example of how science progresses. For centuries, people have watched the aurora and wondered. Gradually, piece by piece, we've built up our understanding. We've gone from thinking the lights were spirits or reflections to understanding them as the visible result of particles from the sun interacting with Earth's magnetic field and atmosphere. And even now, scientists are still making new discoveries, still finding new details and mechanisms that add to our knowledge. The northern lights are a reminder that even phenomena we can see with our own eyes, phenomena that have existed for as long as Earth has had an atmosphere and magnetic field, can still hold secrets waiting to be understood. Here's something that might surprise you. The northern lights aren't unique to Earth. Auroras happen on other planets too. Jupiter has auroras. In fact, Jupiter's auroras are much more powerful than Earth's, because Jupiter has a much stronger magnetic field. Scientists have studied Jupiter's auroras using spacecraft and telescopes, and they've learned that Jupiter's auroras are powered not just by the solar wind, but also by material from Jupiter's moon Io. Io has active volcanoes that constantly send material into space. Some of that material gets caught in Jupiter's magnetic field and contributes to creating auroras around Jupiter's poles. Saturn also has auroras, as does Uranus and Neptune. Even Mars, which has lost most of its magnetic field, can have small, localized auroras in regions where there are remnants of ancient magnetic fields embedded in the crust. Scientists have even detected auroras on planets beyond our solar system. Using powerful telescopes, astronomers have found evidence of aurora-like emissions from planets orbiting other stars. These observations are helping us understand that auroras are a common feature throughout the universe, happening wherever there's an atmosphere, a magnetic field, and a source of charged particles. There's something beautiful about that. The northern lights, which seem so special and unique when we see them dancing over Earth's Arctic, are actually part of a much larger pattern. They're an example of fundamental physics playing out on a grand scale. Wherever planets have magnetic fields and receive streams of energetic particles, auroras can form. They might look different, might have different colors depending on what gases are in the atmosphere, but the basic process is the same. In studying auroras on other planets, scientists have learned things that help them understand Earth's auroras better. And in turn, what we learn from studying Earth's auroras helps us interpret observations from distant planets. It's all connected. Here's something curious that people have reported for centuries. Some say they can hear the northern lights. They describe crackling sounds, popping noises, or rustling sounds that seem to come from the aurora itself. For a long time, scientists were skeptical about these reports. The aurora happens at such high altitudes that any sounds it made shouldn't be able to travel all the way down to the ground. Sound waves need air to travel through, and the air at aurora altitudes is far too thin. It seemed physically impossible for people to hear the aurora. But recent research has suggested that maybe, under certain specific conditions, people really can hear something related to the aurora. Scientists think it might work like this. During strong geomagnetic storms, the changing magnetic fields can cause a buildup of static electricity much closer to the ground, in a temperature inversion layer that sometimes forms about 80 meters above the surface on calm, cold nights. When this static electricity discharges, it can create small cracking or popping sounds. So you're not hearing the aurora itself, which is happening hundreds of miles overhead. Instead, you're hearing an electrical discharge much closer to the ground that's triggered by the same geomagnetic activity that creates the aurora. It's an indirect sound, but it is real. The indigenous peoples of northern regions, who have lived with the aurora for thousands of years, have always known this. In some indigenous languages, there are words that specifically refer to the sounds of the aurora. Western science is just now catching up to this traditional knowledge. See northern lights yourself. Timing and location are important. The aurora is always happening somewhere, but seeing it requires dark skies and being in the right place. The best places to see the northern lights are in what's called the aurora zone. This is a ring around the Arctic, roughly between 66 and 69 degrees north latitude. This includes northern parts of Alaska, Canada, Iceland, Greenland, Norway, Sweden, Finland, and Russia. If you're in one of these regions during the winter months, when nights are long and dark, you have a good chance of seeing auroras. But you don't necessarily need to be right in the Arctic. During strong geomagnetic storms, the aurora can expand southward and become visible from much lower latitudes. Places like Scotland, northern England, and the northern United States can sometimes see the northern lights during particularly active periods. Timing matters too. The best time of year to see auroras in the northern regions is generally from September through March. This is when nights are darkest and longest. The aurora actually happens year-round, but during summer months near the Arctic, the sky never gets fully dark, making it impossible to see the lights. The best time of night is usually between about 11 in the evening and 2 in the morning, though auroras can appear at any time during the dark hours. And interestingly, aurora activity tends to peak around the spring and autumn equinoxes. Scientists aren't entirely sure why this happens, but it has to do with how Earth's magnetic field is oriented relative to the solar wind during these times of year. Of course, you also need clear skies. Clouds will block your view of the aurora, just as they block your view of the stars. And you need to be away from light pollution. The glow from cities can wash out all but the brightest auroras. Finding a dark location, far from city lights, will greatly improve your chances of seeing a good display. There are now many resources available if you want to hunt for auroras. Scientists provide aurora forecasts, predicting when geomagnetic activity is likely to occur. There are websites and smartphone apps that send alerts when conditions are favorable. Some of these forecasts can predict aurora activity several days in advance, giving you time to plan a viewing trip. One of the wonderful things about the northern lights is that you don't need any special equipment to see them. No telescopes, no binoculars, just your eyes and a clear, dark sky. The aurora is large and bright enough to see with the naked eye. In fact, binoculars or telescopes can actually make the experience worse because they limit your field of view. The aurora often spreads across a huge portion of the sky, and you want to be able to take it all in at once. Modern cameras can capture auroras beautifully. If you look at photographs of the northern lights online, you might notice that the colors often look more vivid and saturated than what people describe seeing in person. This is because cameras can collect light over time in ways our eyes can't. A camera using a long exposure can capture fainter colors and more detail than our eyes perceive in real time. When you see the aurora with your own eyes, especially weaker displays, the colors might appear more subtle, more pastel. The greens might look pale, the reds might be barely noticeable. But that doesn't make the experience any less magical. There's something special about witnessing the aurora in person that photographs can't quite capture. The way it moves, the way it fills your entire field of vision, the sense of scale, of seeing something happening in the atmosphere hundreds of miles above your head. The feeling of standing under a sky filled with dancing light, knowing that what you're seeing is the result of processes that span from the core of the sun to the edge of space, to the thin air above our planet. It's a profound experience. Scientists can look back in time and figure out when strong auroras happened, even before anyone was around to record them. They do this by studying ice cores and tree rings. When strong solar storms occur, they increase the amount of certain radioactive isotopes that form in Earth's atmosphere. One of these is carbon-14. Trees absorb carbon from the atmosphere as they grow, and they lock that carbon into their wood. By measuring the amount of carbon-14 in tree rings from different years, scientists can identify when unusually large amounts were produced, indicating a strong solar storm. Ice cores work similarly. When snow falls and gets compressed into ice, it preserves a record of the atmosphere at that time. Drilling deep ice cores in places like Greenland and Antarctica, and analyzing the isotopes trapped in different layers, scientists can identify past solar storms. Using these techniques, researchers have found evidence of extremely powerful solar storms that happened centuries or even thousands of years ago. One event, around the years 774 to 775, appears to have been much larger than anything we've recorded in modern times. Another big event happened around the year 993. These ancient storms would have created spectacular auroras visible over much of the planet, but they happened long before anyone had cameras or even reliable written records, so we can only imagine what they must have looked like. This research is important because it helps us understand how variable solar activity can be. It tells us that the sun is capable of producing storms much more powerful than anything we've experienced in the modern era. And that means we need to be prepared for the possibility that a truly massive storm could happen in the future. The northern lights are beautiful, but do they affect life on Earth in any meaningful way, beyond just being nice to look at? In most cases, no. The auroras themselves don't affect us directly. They happen at such high altitudes that they don't influence the weather or climate near the ground. The particles causing the aurora are absorbed high in the atmosphere, far above where we live. However, the geomagnetic storms that create strong auroras can have effects. As mentioned earlier, these storms can disrupt power grids and satellite communications. They can pose radiation risks to astronauts in space, and during very strong storms, they can even induce electrical currents in long pipelines or cables on the ground. There's also been some research suggesting that major changes in solar activity over very long timescales might influence Earth's climate. But this is a complex topic with many uncertainties. The main driver of Earth's climate is the total amount of energy we receive from the sun, which varies only slightly. The solar wind and geomagnetic effects seem to play a much smaller role, if any. What is clear is that Earth's magnetic field, which makes the aurora possible, is crucial for protecting life on our planet. Without that magnetic shield deflecting most of the solar wind, Earth's atmosphere would gradually be stripped away, and life as we know it couldn't exist. The aurora is a visible reminder of this protective shield at work. So, in a way, the northern lights are a sign of Earth's habitability. They're evidence that our planet has the right ingredients to support life: an active interior that generates a magnetic field, an atmosphere that can interact with space, and a position in the solar system where we receive just the right amount of energy from the sun. Before we understood the science, the northern lights lived in human imagination as something magical and often sacred. Different cultures around the world developed their own interpretations and stories about what the aurora meant. In some Nordic traditions, the aurora was seen as reflections from the shields of warrior maidens who rode across the sky. In other traditions, the lights were believed to be spirits moving between worlds. Some cultures saw them as omens, either good or bad, depending on their appearance. In parts of North America, some indigenous peoples believed the aurora represented the spirits of ancestors, while others had different interpretations specific to their cultural worldview. These stories weren't just entertainment. They were ways of understanding and relating to a natural phenomenon that was both beautiful and mysterious. They helped people make sense of something they could see but not fully explain, and they connected the aurora to the larger framework of how different cultures understood the cosmos and their place in it. Even after science began explaining the aurora, the sense of wonder hasn't diminished. If anything, understanding the actual mechanisms makes the aurora even more remarkable. We now know that those dancing lights represent a connection between our planet and a star 93 million miles away. We know they're evidence of invisible magnetic fields and subatomic particles and physical processes that span the entire solar system. That knowledge adds depth to the experience of watching the aurora. It doesn't replace the wonder with cold facts. It enhances the wonder with a deeper appreciation of how remarkable our universe is. The aurora also continues to inspire art, music, and literature. Photographers chase the northern lights, trying to capture their beauty. Musicians compose pieces inspired by their movement and color. Writers use them as metaphors for transformation, mystery, and the sublime. The aurora has become part of human culture in ways that transcend any single interpretation or understanding. Our understanding of the northern lights continues to grow. Scientists are constantly making new observations, running new experiments, building better computer models. Each discovery adds another piece to the puzzle. One area of active research involves trying to predict aurora activity more accurately. Right now, we can forecast when a coronal mass ejection has left the Sun and roughly when it might reach Earth. But predicting exactly how strong the resulting aurora will be and exactly where it will be visible is still challenging. Better predictions would not only help aurora watchers plan their viewing trips, but also help us prepare for potential impacts on technology and infrastructure. Another area of research involves understanding the detailed physics of how energy flows through Earth's magnetosphere. The magnetosphere is an incredibly complex system, with plasma and magnetic fields interacting in ways that are still not fully understood. New satellite missions helping us gather more detailed measurements, but there's still much to learn. Scientists are also interested in how Earth's magnetic field itself might change over time. We know the magnetic poles move slowly, and we know that every few 100,000 years, the magnetic poles can even flip completely, with north becoming south and south becoming north. During a flip, the magnetic field becomes weaker and more complex, which could affect how the aurora appears and where it can be seen. Understanding these long-term changes is important for understanding Earth's history and future. And as mentioned earlier, studying auroras on other planets is helping us understand both those worlds and our own. Each planet with auroras has its own unique characteristics, and by comparing them, we learn about the fundamental physics that governs how atmospheres, magnetic fields, and charged particles interact throughout the universe. There's something peaceful about thinking about the northern lights, isn't there? Something calming in the knowledge that they're always there, always happening, whether we're watching or not. They don't perform for us, they simply exist. a natural consequence of the physical laws that govern our solar system. The northern lights remind us that we're part of something larger. Earth isn't isolated. We're constantly bathed in the energy and particles flowing from the sun. Our planet responds to this, flexing its magnetic field, guiding particles to the poles, lighting up its atmosphere in shimmering colors. It's a dance that's been going on for billions of years, long before humans existed and long before anyone was here to witness it. And yet, we are here to witness it. We're fortunate enough to live on a planet with an atmosphere and a magnetic field that create this beautiful phenomenon. We're privileged to exist at a time when we can both enjoy the aurora's beauty and understand the science behind it. We can watch the lights dance across the sky and know that what we're seeing is starlight made visible in Earth's atmosphere. We can feel the wonder of the experience and also appreciate the elegant physics that makes it possible. The northern lights teach us about interconnection. They show us that the sun and Earth are linked, that space isn't empty, but filled with particles and energy and fields, that the atmosphere high above our heads is alive with processes we can't normally see. They demonstrate that beauty can emerge from the most fundamental physical processes. They prove that understanding how something works doesn't diminish its magic. As we come to the end of our exploration, imagine for a moment what it would be like to stand under the northern lights on a clear, cold night in the Arctic. The air is still, the stars are brilliant overhead, and then, slowly, a glow appears on the northern horizon. It brightens. It spreads. Curtains of green light begin to rise, swaying gently like silk in a breeze. Purple edges appear. The curtains ripple and flow. The light brightens until it fills half the sky. You watch, knowing that what you're seeing is sunlight, in a way. Not the direct light of the sun, but the sun's energy transformed, carried across 93 million miles of space by particles traveling at 1 million miles an hour, captured by Earth's magnetic field, guided to the poles, transferred to oxygen and nitrogen atoms in the thin air hundreds of miles above your head, and finally released as visible light that travels down to your eyes. You watch, understanding the science, but also simply experiencing the beauty. The two aren't in conflict. The science enhances the experience, adding layers of meaning. The aurora becomes not just a pretty light show, but a visible manifestation of invisible forces, a window into the workings of our solar system, a reminder of how remarkable our universe is. And maybe that's the most important thing about the Northern Lights. They invite us to pause, to look up, to wonder. In a world where we're often focused on immediate concerns and everyday details, the aurora asks us to think about bigger things. About the sun that warms our planet, about the magnetic field that protects us, about the atmosphere that surrounds us, about our place in a vast cosmos filled with wonders. The Northern Lights have been dancing in Earth's sky for billions of years. They'll continue to dance for billions more, long after we're gone. They're patient, eternal, indifferent to our observations, yet generous in their beauty whenever we choose to look. Tonight, somewhere near the Arctic, the aurora is shimmering across the darkness. Someone might be watching, or perhaps no one is. It doesn't matter to the lights. They dance regardless. A quiet conversation between star and planet. A light show written in the language of physics and painted across the sky in colors that speak to something deep in the human heart. Thank you for joining me on this gentle journey through the Northern Lights. Whether you're still wide awake, comfortably drowsy, or already beginning to fade into sleep, I hope you found something in this exploration that resonated with you. Something that sparked your curiosity, or eased your mind, or simply gave you something beautiful to think about. The aurora borealis, the northern lights, whatever name you prefer, they're waiting for you if you ever get the chance to see them. They're patient, and they're spectacular. Until then, you can rest knowing they're out there, somewhere, painting the Arctic sky in colors that humans have watched and wondered at for thousands of years. You've learned enough for tonight. You've taken a journey from the heart of the sun to the thin air above Earth's poles. You've explored magnetic fields and excited atoms, colors and curtains of light, the connection between worlds. That's plenty to carry with you as you drift towards sleep. Close your eyes now, if you haven't already. Let your breathing slow. Let the images of dancing green light play gently at the edges of your thoughts. Imagine those soft curtains rippling across a dark sky. Imagine the quiet cold of an Arctic night. Imagine standing under that eternal light show, feeling small and connected all at once. You have done enough for today. You have wondered enough, learned enough, imagined enough. The northern lights will keep dancing while you sleep. Earth's magnetic field will keep protecting. The sun will keep sending its gentle wind of particles across space. All of it will continue, patient and eternal, while you rest. Let yourself sink deeper now, into comfort, into stillness, into the soft darkness behind your eyelids, where thoughts become dreams. The aurora is beautiful, but so is rest. So is peace. So is the simple act of letting go and allowing sleep to carry you wherever it will. Sweet dreams. May your rest be gentle, and may the northern lights dance in your mind's eye. Soft and beautiful, a reminder that the universe is filled with wonders, waiting to greet you when you wake. Good night.